Hello everyone, welcome to the Better Science channel. My name is Xiaoli Zhang and I'm one of the application engineers at Better Science Instruments. Have you ever wondered how to measure the particle size of nanoparticles? What techniques is employed and how to interpret the results? Follow me with this detailed walkthrough on the introductions to dynamic light scattering for nanoparticle size analysis, also known as the DLS technique. First, we will start with the theory of DLS to understand how it works. Light scattering exists in many aspects of our daily life. For example, we can enjoy the beautiful scenery of sunsets thanks to the light scattered by tiny molecules in the atmosphere. But what exactly is light scattering? Light waves are considered of both an electric field and a magnetic field, with the two fields propagating perpendicular to each other. Therefore, one can consider a light wave as an electromagnetic wave. When a monochromatic and coherent light source irradiates onto the particle, the electromagnetic wave will interact with the charges in atoms that compose the particle, and thus induce the formation of an oscillating dipole in the particle. The resulting oscillating dipole emits electromagnetic waves in all directions, changing the original propagating directions of the incident light. Light scattering refers to this emissions of light from oscillating dipole. During quasi-elastic light scattering, the frequency changes between scattered light and the incident light are small, and the light scattered by the oscillating dipole has a spectrum that broadens around the incident light frequency. The scattered light intensity depends on the particle's intrinsic physical properties such as size and molecular weight. The scattered light intensity is not a constant value. It fluctuates over time due to the random walk of particles that are undergoing Brownian motions. The fluctuations in scattered light intensity with time allows us to calculate the diffusion coefficients through the autocorrelation functions analysis. Then, using the Stokes-Einstein equations, the particle size distributions can be calculated from the diffusion coefficients. This technique is called the dynamic light scattering, abbreviated as DLS. By analyzing the fluctuating scattered light intensity due to Brownian motions, DLS can obtain the particle size distributions of small particles suspended in a diluted solutions. Typically, the measuring size limit of DLS falls in the nano and submicron range, with the magnitude of 1 nanometer to 10 micrometers. There are several advantages of using the DLS when sizing nanoparticles. First, DLS is non-invasive to the samples, meaning that the structure of the molecules would not be destroyed during sizing. A small amount of samples is sufficient for diluted solutions preparations. With the DLS method, results with great repeatability and accuracy can be obtained within a few minutes. The testing process is nearly all automatic, minimizing operation errors from different operators. With DLS, the particle size distributions can be measured at different temperatures, and thus a thermal analysis can be conducted on the test sample. DLS provide various industries the opportunity to control their product's quality and therefore maximizing product performance by controlling particle size. These industries include but are not limited to semiconductors, renewable energy, pharmaceuticals, inks, pigments, batteries, and etc. As we mentioned previously, the fluctuations in scattered light intensity are due to Brownian motions of the particles. Brownian motions refers to the particle's continuous and spontaneous random walk when placed in the medium, resulting from the collisions between the particles and the medium molecules. To quantify the speed of Brownian motions, the translational diffusion coefficient is modeled by the Stokes-Einstein equations. Notice here the diffusion coefficient is specified by the word translational, indicating that only the translational but not the rotational movement of the particle is taken into account. The translational diffusion coefficient has the unit of area per unit time, where the area is introduced to prevent the signs change convections when the particle is moving away from its origin. The Stokes-Einstein equation is expressed as follows: dt equals kBt over 6 pi eta r, where kB is the Boltzmann constant, T is the temperature in kelvins, eta is the viscosity of the medium, and RH is the hydrodynamic radius of the particles. Hydrodynamic radius refers to the effective radius of a particle that has identical diffusions to a perfectly spherical particle of that radius. For example, as seen in the figure on the left, the true radius of the particle refers to the distance between its center and its outer circumference, while the hydrodynamic radius includes the length of the attached segments since they diffuse as a whole. When collided with medium molecules, a particle with larger hydrodynamic radius is less likely to be moved an extra distance, thus resulting in a smaller translational diffusion coefficient, and vice versa. Now we know how DLS works, let us take a closer look at its optical setup. Typically, a DLS setup contains four most important components: the light source, light scattering cell, the detector, and the hardware unit. The light source emits a coherent light beam and irradiates it onto particle suspensions in the light scattering cell. The detector unit detects and collects scattered light intensity fluctuations at a set angle from the light scattering cell. The correlator analyzes the autocorrelation functions of the fluctuating intensity and eventually calculates the hydrodynamic radius of the sample particles in the data processing software. In the next few slides, we will consider the laser source, detector, and correlator in details. The light source of the optical system is typically a laser device that emits a monochromatic, coherent, and amplified intensity light beam. The laser device utilizes energy supplied by the pump force, such as electricity, light, and chemical reactions, to generate an amplified intensity laser beam, with power ranges from milliwatts to watts. When light passes through the gain medium in the laser device, a process called simulated emissions allows the emissions of photons from the gain medium molecules. Therefore, the gain medium serves as a source of photons needed to create a light beam inside a laser device. According to the different materials of the gain medium, laser devices are categorized into 4 different types. If the gain medium inside a laser device is a gaseous mixture, the laser is called a gas laser. Typical examples of gas laser include helium neon laser, which emits laser with a wavelength of 632.8 nanometer, argon ion lasers, and carbon dioxide laser. A solid-state laser refers to a laser device where a solid acts as the gain medium. In a solid-state laser, small amounts of solid impurities called dopant are added to the gain medium to change its optical properties. These dopants are often rare earth minerals such as neodymium, chromium, and ytterbium. The most commonly used solid-state laser is neodymium-doped ytterbium aluminum garnet, abbreviated as NDYAG. There are also liquid laser and semiconductor laser, which have a gain medium of liquid solutions and semiconductor material, respectively. The majority of the laser devices in DLS instruments are gas lasers and solid-state lasers. Gas laser has the advantage of stable wavelength emissions with relatively low cost. However, a gas laser usually has relatively large volume that makes it very bulky. On the other hand, a solid-state laser is smaller in size and also less heavy, making it more flexible to handle. After the laser beam irradiates onto the sample cell, light is scattered by the particle, and this scattered light is fluctuated because of Brownian motions. A highly sensitive detector picks up these scattered light fluctuation signals at even low intensity levels and converts them to electrical signals for further analysis in the correlator. Commonly used detectors in an optical setup of DLS include photomultiplier tube and avalanche photodiode. According to Lawrence W.G. et al., PMT and APD have similar noise-to-signal performance at most signal levels, while the APD outweighs the PMT at red and near-infrared spectral regions. APD also has higher absolute quantum efficiency than PMT. Because of these reasons, recently APD is being more frequently utilized in DLS devices. The angle formed between the detector and the sample cell is called the detection angle. The most common one is single-angle light scattering detections, where only one detector captures light at a certain angle from the sample cell. The detection angle must be greater than 20 degrees, and most devices use 90 degrees or 173 degrees. Besides single-angle scattering, there is a setup called multi-angle light scattering, abbreviated as MALS. MALS can simultaneously detect scattering light intensities at various angles. Unlike single-angle light scattering, the detection angle for MALS can be as low as 1 degree. One standard method to set up a MALS is to set up multiple detectors and optical fibers surrounding the sample cell. Detectors at larger angle can better capture faster diffusion motions from smaller particles, thus more sensitive for smaller particle size distribution determinations, and the same is true for smaller detection angle and larger particles. After the optical setup, the process of scattering and collecting light intensity is complete. The signals detected by the detectors are then analyzed in the correlator to eventually calculate the hydrodynamic radius distributions. What does the correlator do? Does it just magically take in scattered light intensity and outputs the hydrodynamic radius distribution like a black box? In the next few slides, we'll discuss the computations inside the correlator and understand the mechanics of hydrodynamic radius calculations. Notice here that in order to simplify the calculations, all the computations mentioned here are based on two major assumptions. First, the samples are monodispersed, or having uniform shape and size over the whole population. Second, only the translational diffusion coefficient is taken into account during the calculations. If one wishes to measure the size of rod-like particles where rotational movement dominates over translational movement, a depolarizer can be employed after the laser source. In this presentation, we will only focus on the translational motions and will not touch details on the rotational motions. First, we must realize that the light intensity depends on the scattering vector, q, and time t. Q can be calculated as 4 pi n over lambda times the sine of theta over 2. In this equation, n is the refractive index of the medium, lambda is the wavelength of the incident light in vacuum, and theta is the detection angle. Therefore, if values of all three parameters are known in a single angle scattering setup, the scattering vector q will be a known constant. And we can express the scattered intensity as a function of q and t, or I equals to fqt. After obtaining the scattered intensity, we can multiply it with itself after it has been shifted by some arbitrary interval tau in time. This tau can be anything between a few nanoseconds and microseconds, but the actual value of the time interval does not affect the test results. Using the multiplied intensity, divided by the average intensity over total measurement time, represented by a bracket between the intensity squared, as shown in the equation on the right here. This expression is called the autocorrelation function, or G2Q tau. It has a single exponentially decay from 2 to 1. With G2Q tau, one can relate to the amplitude correlation factor G1Q tau with the Sickert relations. Beta times G1Q tau to the square equals G2Q tau minus 1. G1Q tau, on the other hand, single exponentially decay from 1 to 0, with 0 meaning there's no correlation at all between the signals at time t and time t plus tau, and 1 meaning perfect correlation. Here, the product of q squared and diffusion coefficient d is called the decay rate, represented by symbol gamma. Finally, with all the known information of the correlation function, the hydrodynamic radius can be computed using the Stokes-Einstein equation. What does it mean to be mono and polydispersed, and why is it important? Monodispersed particles are all identical in size, shape, and mass, resulting in one narrow peak in the particle size distribution. On the other hand, polydispersed particles are not uniform in those parameters. It is important to realize the polydispersity of the samples because the algorithms of calculating hydrodynamic radius distributions in the correlator are different depending on whether the samples are monodispersed or polydispersed. If samples are polydispersed, the correlation function G1 is no longer a single exponentially decay function, but an integral over the decay rate gamma. Two main mathematical algorithms are used to solve this integral. The first and most common one is the cumulants method. Using Taylor series expansions on the natural logarithm of the integral, the cumulants method can compute a z-average diffusion coefficient and thus the average hydrodynamic radius. When using this method, be careful not to overfit the parameters by considering too many coefficients, kappa, since overfitting might render all parameters to be less precise. However, the cumulants method is only valid with samples that have small size polydispersity. Validations of the calculations can be done by computing and checking the polydispersity index, or PDI. PDI is calculated as kappa 2 over kappa 1 squared all under the square root, and the cumulant analysis is only valid if the PDI value is relatively small, or if the particle size distribution is sharply peaked. The Contine algorithm can directly compute the integral and is theoretically able to compute the hydrodynamic radius distributions for samples that are widely dispersed. It is a relatively complicated mathematical method involving regularization. Properly preparing the samples is one of the key factors to successful nanoparticle sizing. In the next few slides, I will go over some important aspects during sample preparation. Before preparing the samples, there are a few requirements about the sample solutions that need special attention. First, look up the viscosity and refractive index of the solvent in advance to test, since they are key parameters in the Stokes-Einstein equations and will affect the results. Nowadays, most DLS devices come with built-in viscosity and refractive index values for common solvents. If the solvent chosen to prepare the solution is less common, make sure its properties are obtained before proceeding to the test. As mentioned at the beginning of the slides, one of the advantages of DLS technique is thermal stability analysis. If one desires to measure particle size distributions under different temperatures, utilize the temperature control functions in the DLS device to maintain the solutions at a preferred temperature. The concentrations of the samples should be as dilute as possible to ensure the validity of the Stokes-Einstein equations. If the sample's concentration is high, particle interactions could not be neglected, and the Brownian motions of particles will not be solely due to random collisions at this point. But the concentration should be large enough to create a sufficient amount of scattered light intensity, such that the detectors can capture enough information about the intensity fluctuations. Be careful of the changes in zeta potential when diluting the solution. Zeta potential is an important indicator of the stability of the suspensions. A system with higher zeta potential is more stable and less likely to form agglomerate because of the repelling of counterions on particle surfaces. During dilutions, monitor the pH, concentration of surfactants, and conductivity of the solutions to prevent dramatic change in zeta potential, which will lead to particle agglomerations and an overestimation of particle size distribution. The solvent used to prepare the sample solution should also be considered. Depending on different types of particles, the choices of solvents are also different. However, the solvents that will interact with a solute. For example, a solvent that will form aggregates or mixed with the solutes should not be chosen for solutions preparations. If the samples are polyelectrolytes that possess Coulomb interactions between particles, the scattered light intensity might be influenced. To disturb the potential Coulomb interactions, add an adequate amount of salt into solutions without changing the solvent's refractive index. The most important step in preparing a sample solution is to remove impurities such as dust particles. These impurities also undergo Brownian motions in solutions and will contribute to scattered light intensity, which will lead to an overestimation of size. To remove the dust particles, rinse the solution containers thoroughly with acetone and air dry it in a dust-free fume hood before transferring the solutions into the container. In the DLS device, disposable plastic cuvettes are usually used at the sample cells. These cuvettes are mostly made from polystyrene or polymethyl methacrylate, where PMMA is more chemically resistant than PS. When preparing the sample solutions, one should consider its properties before choosing a suitable type of cuvette. If the samples are corrosive or precious, use the microvolume PMMA cuvette where only a small amount of sample is needed for testing. Otherwise, it is recommended to choose the common PS cuvette because it is more economically sustainable due to its low cost. Before using the cuvette and its lid should be rinsed with acetone thoroughly and air dried in the dust-free fume hood. A disposable syringe with cartridge filters should be used to remove dust particles in the solutions before performing the DLS test. If the solvent used in solutions is organic, one should use a glass syringe instead of a plastic syringe. Similar to choosing sample cells, one should choose the pore size of filter membranes according to the particle properties. The pore size should be larger than the particles, such that only the sample particles can go through, but not the dust particles. High pressure might be exerted onto particles inside a syringe during the filtration process. It might lead to crushing or destruction of particles and affecting the accuracy of particle size analysis. The prepared solution is then transferred to the sample cells and ready for testing. The steps are as follows. Transfer the solutions to the syringe with cartridge filters to perform filtration. To avoid overpressurizing and destroying the particles, filter 1 drop of sample solutions per second. Discard the first 1 to 2 drops of filter solutions because the dry membrane might absorb some scattering particles upon contact with the sample solutions and thus affect the concentration of the solutions. Filter the rest of the solutions into the disposable cuvette either by inclining the cuvette by 45 degrees or directly drop to the cuvette. Inclining the cuvette minimizes the formation of air bubbles, but it requires the cell wall to be extremely clean. Directly filtering droplets into the cuvette prevent contact with the cell walls but might form air bubbles. Therefore, one should perform filtration carefully with either filtration method. After filling the cuvette with the solution to the desired height, carefully cover the cuvette with its lid and place it into the sample holder. The last part is the DLS results interpretation. Interpreting results can aid us in evaluating the quality of the particle size test and also obtain information about the particle size distribution. The quality of the correlation function should be checked before proceeding to the particle size analysis, since it directly relates to the accuracy of the particle size result. The overall shape of the correlation functions could well indicate its quality. As shown in the Lesmo figure, if the correlation curve is a smooth curve exponentially decaying from 1 to 0 without presence of noise, it suggests that the correlation was well performed and it is good to proceed to the particle size distribution analysis. However, if the curve is still overall smooth with some level of noise, as shown in the middle figure, it might be due to the presence of impurities in the samples that affect the repeatability of the results. Under this scenario, the operator can filter the sample solutions with the appropriate syringe pore size again to remove the impurities, such as big dust particles in the solutions. When the scattering is insufficient in a test, its correlation function curve will look like the curve in the rightmost figure. In this case, the maximum value of the function is much less than 1, and it does not exhibit exponentially decay behavior. The operator could increase the sample concentrations or the number of subruns to increase the amount of scattering. DLS reports results in Z-average particle size, which is a scatter intensity weighted size. It comes from the fact that when computing the correlation function integral using the Cumulants and Conti method, an average translational diffusion coefficient is obtained, and thus resulting in the average hydrodynamic radius from the Stokes-Einstein equation. The Z-average particle size validity should be checked with the polydispersity index, or PDI. As shown in the table, a sample results report of particle size from DLS includes a Z-average particle size with uncertainty and the PDI value corresponding to that Z-average particle size. If the value of PDI is large, indicating that the samples are possibly polar dispersed, then the Z-average particle size is not a fully representative description of the given sample. According to the ISO 22412-2017 particle size analysis of dynamic light scattering, the particle size result should be reported along with its uncertainties and repeatability. The measurement uncertainty is expressed by the standard deviations, while the repeatability is the relative standard deviations that describes how close the results obtained from multiple measurements are to each other within each run of test. As regulated by ISO 22412-2017, monodispersed materials with diameters between 50 nanometer and 200 nanometer should have Z-average particle size with repeatability less than 2%. Let's wrap up what we're covered in this presentation. First, we went over the theory of light scattering and DLS, explain how does the Brownian motions come into particle size determination. Then we look at the optical setup of a typical DLS device and discuss the laser source, correlator, and the detector in the details. Moving on, we examine the sample preparations for the DLS test, including making and filtering the solutions, removing impurities, and choosing sample cells. Finally, we went over how to interpret the results obtained from the DLS test. Here are the references used to build up this presentation. Thank you for listening. I hope you found this presentation helpful. If you have any questions, feel free to email me at shelly.zhang@betterscience.com. Please don't forget to subscribe to our channel. For more information, visit our official website www.betterscienceinstruments.com. Until next time, bye!